Howdy, everybody. Hi. We're here to talk about the 2019 robot. Talk a little bit about all its quirks, its nice advantages. Real quick, do you want to do intros or you just want to? I'm gonna have to sit in the corner sometimes.
Okay. So my name's Rishon. I'm a senior this year. It's my 4th year on the team, and I am currently CAD lead.
Hi, I'm Sabina. This year I am team captain. It is my 6th year. I joined in with my brother when they used to allow middle schoolers, so I'm having a great time. It's senior year. Get ready to party.
This robot's name is Tachyon. The reason behind this was a tachyon is a small particle that travels faster than the speed of light, and a robot is extremely small and fast. So the obvious connection right there. So a couple of subsystems we're going to talk about today. We're going to start with the drivetrain, and then the elevator, the wrist, the intake, the entire suction system, which consists of both the suction pump and the suction cups, and then the stilts, which is our climbing mechanism, and then vision and cameras, which is what Sabina's going to talk about.
Absolutely.
Okay, so the drivetrain. Our drivetrain is a West Coast drive, and like I said, our robot was intended to be extremely small. So as a result, our frame size is 25 inches by 19 inches, which is extremely tiny compared to other FRC robots. The drivetrain itself is a 6-wheel drop center with 4 4-inch Coulson wheels, 2 in the front, 2 in the back, and 2 tread wheels in the middle. And the reason we use tread is it gave our robot more traction, meaning that we would slip less during auto modes, causing less mistakes. And then as for the transmissions, there are 2 single-speed transmissions. Each are powered off of 2 regular sims with 1 reduction. The reason we were able to do something this small and compact was because of how light our robot is. We didn't need the acceleration that came with 3 mini sims and used 2 regular sims instead. And again, that 1 reduction just let our transmissions be extremely tiny.
Yeah. And then in terms of sensors, we have standard US digital rotary encoders on each transmission, plus we have an IMU. I believe they are from Analog Digital. It's the one that they used to sell in 2015 or 2016, and it just has pretty much what a gyro has, a little bit extra. We also have the Spartan board on our Robo Rio, which is sold by WCP, and that we also use that gyro, so lots of information for driving.
Alright, so this is a picture of our drivetrain windows being assembled a little ways in the season. So as you can see, the majority of it is made up of tubes, and the reason we were able to do this is because we have chains running our drivetrain, and these chains are housed inside of each tube. Sorry about that.
This is going to be really fun.
Okay, so our drivetrain tensioners. We had to do something a little bit different this year because we were using chain. In past years, we've used belts along with the clamshell drivetrain frames, and the reason we use chain is because we were able to, first of all, tubes are extremely small, and we were also able to manufacture the majority of our tubes in-house using our mill, versus having to send out a clamshell drivetrain frame to a sponsor and then waiting for it to come back. The way that we tensioned our drivetrain shafts was using a snail shell cam, which you can see right here, and then a tensioner assembly, which is this whole thing right here. And so as you turn the snail shell cam, it pushes the entire tensioner assembly outwards, pushing the drivetrain shaft outwards and thereby tensioning the chain. So this was a little bit of a finicky process because we only had the snail shell cam on one side of our drivetrain. There isn't any room on the other side because of the wheel. And this meant that we had to be really precise and really careful when we were tensioning our drivetrain, because if we did it wrong or over-tensioned it, our drivetrain shaft would be twisted inside of the tube, and that would cause unnecessary friction and cause our robot to move slower than it really should. And this actually did end up happening to us for a couple matches at Utah before we realized what the problem was. Our robot was driving a lot slower than it should have, and our driver was like, something's off, we need to fix this. Okay, so the elevator. The elevator is made using carbon fiber tubes, which are extremely light and stiff, and the entire elevator assembly weighs about 14 pounds. And the elevator gearbox is extremely tiny and well packaged, and because of how light everything is, we were able to get away with it being powered by one 775 Pro and it having 1 reduction. So this is a CAD model from the bottom view of the elevator gearbox. You can see how thin this gearbox is because there's only 1 reduction inside of it. So it's really nicely packaged in the center of our robot. And then these are the carbon fiber tubes. This is the first stage of our elevator. You can see the pulleys over here that are used to string it, and the bearing blocks on the sides. So the elevator itself is a two-stage continuous elevator.
Yeah, and then in terms of sensors, most of the joints on our robot will kind of have a standard situation every year. So usually we use a potentiometer and then an absolute encoder. So that way it's more precise, and it also makes it easier for zeroing the robot when you first turn it on.
Okay, so a couple pictures here. So this middle picture right here is the elevator when it was being assembled throughout the year. So you can see the gearbox at the bottom, the tubes that were being used to mount to the drivetrain, and the entire elevator assembly up here. So like all subsystems, our elevator wasn't perfect when we first assembled it. We had two main problems. So the first was our robot, one of our main goals for this robot was to be able to score both front and back. And the way that we did this is by using our wrist, which is able to do a full 180-degree motion. However, in order to do that, the carriage, which has the gearbox that's powering the wrist, needs to be at the top of the first stage at all times, so that the wrist can do its full range of motion without actually hitting the elevator. Originally, we planned on keeping the carriage at the top by putting Velcro on our grounded stage and Velcro on the bottom of our first stage to keep it in place while the carriage moved upward. However, because of how light everything was, when the carriage moved upward, it would cause the first stage to move up with it, which really wasn't good for what we were trying to do. And then another problem that we had was because of the way our elevator is strung, we have two strings on the carriage, one in the front and one in the back. And again, because of how it's strung, the forces are not equal on both sides. And what this meant is that the carriage was kind of twisted in the entire elevator frame in one direction, causing friction and causing us to burn out, I think, about 10 775 Pros over the course of the season. So we were able to solve both of these problems with the use of constant force springs, which you can see right here. They were mounted to the first stage and onto the carriage. And for those of you that don't know what constant force springs are, it's a spring that exerts a constant amount of force for its full length of travel. So what these did is they allowed the carriage to be, they constantly pulled the carriage up, keeping it at the top of the first stage at all times. So that solved our wrist problem. And then it also alleviated some of the load of the carriage on the elevator gearbox, meaning that the carriage wasn't twisted in the elevator at all times. So, yeah. Okay, so the wrist. The wrist consists of two parts. One is the gearbox that is housed within the carriage, and if you go to the next slide. The other part is this 3D printed assembly, some telescoping tubes, and then the suction cups on the end. So the entire wrist, the gearbox is packed into the carriage, like I said, and is powered off of one bag motor. And the telescoping tubes, what that means is essentially if you push on the, Sabina, if you want to push on the wrist, so the tubes go inside of the 3D printed assembly and are pulled back upwards by surgical tubing. So the reason we did this is because we run our robot into the game objects and the cargo ship and the rocket really hard over the course of the matches. So if it was in a fixed position, it would have been completely destroyed by now. But the telescoping tubes absorb a lot of the force that the robot is exerting on it by driving full force into game things. So, yeah. Okay, so our ground intake. We had a ground cargo intake, and the way that this one worked is it was off of a 4-bar linkage, if you want to move that out. So basically what that let us do is it let us stow the intake inside of the frame perimeter and then extend out really quickly. And the sides are also made out of polycarbonate, which is really flexy. So the reason we did this is because if we were ever caught off guard with our intake outside of our frame perimeter and we were hit by another robot, we didn't want our intake to explode on impact. A lot of that force is absorbed by the wobbliness of the polycarbonate.
And the only difference between the intake in terms of electrical is the fact that because the intake moves around a lot and we didn't really need precision for it, we only use a standard absolute encoder on it that's part of the gearbox, which we're going to talk about.
Okay, so this is a CAD model of the intake. So the entire 4-bar linkage is powered off of this one versaplanetary gearbox that you can see right here. For those of you that don't know, versaplanetary gearboxes are extremely tiny and compact gearboxes inside this little square assembly right here. And this is in contrast to all of the custom gearboxes that we have on the rest of our robot. And what this let us do is it let us have the entire gearbox in one tiny compact package, which is great for how little room we had on the robot. And then the rollers themselves are run off of 1775 Pro, whose gearbox is housed under that Lexan strip on the side of the bar. Again, really well packaged, and it was really great for us in terms of space. The rollers themselves are have mini Omni wheels on them. Yeah. Okay, so the suction system. The suction system is completely powered off of this one suction pump. The pump is powered off of 1775 Pro. Originally, the pumps were made to work with 700 series motors, but we adapted them for 775s by machining our own cams for them.
Yeah, in terms of how we run and use the suction, we started the season running it always on full power. We quickly realized that that is the best way to burn out a 775 Pro besides using the elevator without a spring. So we said, how do we fix that? So what we have is a pressure gauge on our robot, and essentially we look for suction, and as soon as we find a certain amount, we drop from 8 volts when we're trying to intake something to around, I think, 3.
Okay, so on the other end of the suction system are our 2 suction cups. One is this larger suction cup that has these green bellows that you can see right here with a 3D printed lip that increases the area of the suction cup and some foam that's mounted on the outside. So the bigger suction cup was used for both cargo and hatch panels, and we had a smaller suction cup that you can see over there that was used to complement this for hatch panel. If you go on to the next slide. So it was a lengthy prototyping process to get to the suction cup that we had on the robot. We went through about 27 prototypes to settle on the final version. And a notable prototype that we had was kind of a suction cup with mini Omni wheels on its outside. It's this guy right here. And what this let us do is, even at whatever angle that the robot was approaching the cargo, the suction cups would kind of roll onto it and make it grabbing that game piece that much easier.
The way we solved that issue that we were having before, we realized that these Omni wheels were breaking off, and we thought, is there a different solution? We were watching one of the regionals, and we saw a human player stick a disc into the human player slot and then throw the balls in and let them sit there. We realized that if the balls aren't moving, you don't have this issue. You can move the balls however you'd like, move the robot, it doesn't matter. So we just decided to get rid of the Omni wheels and just have our human player sit there with the ball.
Okay, so this is another part of the suction system is kind of the midway between the cups and the pump are the 2 solenoids that we have mounted onto the wrist. And what these do is they essentially control the flow of vacuum within the system. And you might be asking, why are they mounted on the wrist rather than the belly pan? And the reason behind this is we wanted to minimize the distance between the solenoids and the cups. And basically, the way that vacuums work is the further the distance away from the between the solenoids and the cup, the longer it takes for you to seal onto game pieces and release them. So it was crucial for us to seal onto game pieces and release them as quickly as possible, so we could place very quickly and grab pieces from the human player station very quickly. So, yeah.
That is a problem we quickly learned was very important.
Okay, the stilts. This is my personal favorite part of the robot because I worked on it. So as you can see in this little GIF that I made, the robot is, the way the stilts work is they have these 2 feet that are stowed in the robot for most of the match. And when it's time to climb, these feet are attached to tubes that run through a gearbox and push the entire robot up until it reaches a certain height. And then these feet collapse inwards, and the robot nosedives onto the platform and then lifts the stilts up again and drives forward. So this is a little CAD model of just the stilts you can see here. Okay, so the way that the stilts work is through an over-centered spring system. So I have a little model right here, but basically for most of the match the stilts are kept outwards like this with the feet down, and they're stowed in the robot. And then we have this tube right here that has belt clamps on both the top and the bottom, and this belt is run through our stilts gearbox that you saw in that CAD model back there. So basically through the belt running through the gearbox, the tube moves downwards through the gearbox, and when it reaches a certain height, these springs right here and this standoff right here reaches a Lexan plate right here. And that's kind of like a slide. It slides the standoff out, bringing it up and causing it to go back up to this position. And that standoff with the spring on it is attached to the stilt foot right here via this tube. And basically when that standoff gets pulled upward, the stilt foot also comes back upward. So it's pretty cool. One thing that we ended up doing to the stilts at competition was we realized that the springs weren't really doing enough to lift the feet all the way up, so we added some surgical tubing onto it. So like I said before, like any subsystem, it wasn't perfect. One of the first problems that we identified when we first assembled it was we have these little Delrin blocks that are kept on either side of the stilt tube, so that it's constrained in place, but also can slide with minimal friction. However, because of the way that we dimensioned the Delrin blocks, they were a little bit too thick, meaning that they were pressing in on the tube and just making it harder for it to slide up and down. So it was a little bit of oversight on our part, and we fixed it by shaving them down on the mill. Another problem that we had was at our first regional, which was SFR, and so after a couple matches, we were inspecting the stilts, and one side of the stilt foot was not in line with the other side, and after a little bit of investigating, we realized that the belt on one side of the stilt's gearbox had slipped by 1 or 2 teeth, and what this means is that the stilt feet were not aligned, so it meant that our robot was kind of being tilted as it was climbing. We fixed this by slipping them back in place, but also by making these little belt clamps that were hung off of a standoff inside of the stilt's gearbox, and those essentially pressed the belt onto the pulley to prevent it from slipping again. And then another adjustment that we made was we added these heels. So it's a little bit confusing to see right here, but essentially when we were because of how small our robot was, we were doing a lot of maneuvering on the platform to make room for other robots that could con to level 3. And because our drivetrain is drop center, our robot was rocking back and forth a lot and made it harder for us to position ourselves in the right spot. So we added these heels, and essentially what they did is when the stilts were all the way down, they pushed this entire heel assembly downwards and lock it in place, and this made it so our robot would rock less and it was easier for us to move around. So the way that this works is we have this one giant Lexan piece over here, and a smaller Lexan piece that's riveted to the larger Lexan piece. It's kind of hard to see, but this smaller Lexan piece, those edges can pull up, and the entire thing slides over these 2 standoffs right here. And then there's a standoff on the stilt, so you can't really see. Yeah, that one right there. When the stilts come all the way down, that standoff pushes this entire Lexan assembly downwards. The edges slide off of those standoffs and then flat back into place, and then that locks it in place. So yeah.
Yeah, and if it's not super making sense to you why we have them, just imagine like little baby skis for our robot. That's essentially what we made. Okay, here's the interesting part. I'm not going to get into too much detail because it's kind of really complicated, but essentially in the 971 way of because we can, we obviously had to have a custom vision system because it wouldn't be 971 if it wasn't custom. So, to give you a really brief run through, what's going on with our electrical is we have a whole bunch of cameras. So the Javois cameras are amazing, but their cases wiggle the camera. You can wiggle the cameras inside with the cases. So of course, what are we to do but make a custom 3D printed case with a custom 3D printed heatsink with a custom lens apparatus on top that has an IR filter on it. And then of course, if you have an IR filter, you need an IR light board. And why would you buy one when you could custom make one? So we have a custom made IR light board. So that's kind of what's going on. And you have around 5 of those. So there's 2 in the front, there's 1 on each side. And of course you have to angle them so you can actually see the target versus just seeing the wall. And then there's 1 in the back. And then there's 1 finally in the front, but this one actually doesn't have any IR on it. It's just a normal light, or a normal camera. And that is purely just for the driver, because you know, the driver's the backup, right? So you need one thing. And essentially all the programming that goes into that. We have SPI going to the RoboRio, but there's kind of a lot of cameras and a lot of power going on. So the serial and the USB goes to a custom, it's kind of hard to see, but there's a custom board that handles all of our UART stuff, and that's in the front of the robot because we didn't have that much space. And all of that filters and puts everything into SPI for the RoboRio to understand. In terms of the programming, we're using full field localization for this, but it uses an extended common filter and it's looking for the targets as well as we start in a specific place every match, and from there we can discern exactly where we are, and then we also use the IMU data, the gyro data, and the encoders because redundancy is important. And in terms of how we look at all of the different targets, Of course, it's 971. Why would you use some other blob detection somewhere when you could custom make your own? So that's what we did. It took plenty of time. We had a little issue with light and trees, but we made it through that. It's fine. And essentially that's kind of what we got going on. It's a brief run through. Very simple, not too much.
All right, thank you for coming to our talk. If you have any questions, feel free to ask them now.
Yeah, we will take as many as you want. Also, if you want to look at the robot. You had a question?
How did you realize you needed 2 suction cups for the hatch panel?
So during prototyping, we tried a couple different designs. One was just a single suction cup at the top, but we realized if we wanted to be able to go both ways, if you have one suction cup, the disc will actually rotate all the way around, and we had an issue with it falling off. So then we tried 3 suction cups. Turns out it's kind of hard to hit the disc exactly where all 3 suction cups stick on, so that's how we decided to do it. If you also want to see the robot, it's kind of interesting.
Yeah, you guys can come up in like groups of 3 or something like that.
So maybe I missed it, but for the lift, what are you actually using to power it down, and what sort of gear ratio are you using?
So the stilts, both, we have 2 gearboxes on both sides. Both of them are run off of 1775. I don't know the gearbox exactly. It's a huge gear ratio because these stilts are carrying the entire load of the robot with them. So, but yeah, 1775.
Alright, cool.
Hi, I am Sabina, a student on Team 971. We hope you enjoyed this video. For more videos and resources, please subscribe and visit our website, frc971.org.